Welcome to a lesson with Dr. Powell. Let's take another look at this example that we had where we ran a Gram-Schmidt process on these vectors and we obtained these, and we did so using vector projections where we had a vector v and we were thinking about how to project it onto some u. We found the projection vector like this. We could subtract it off and get something that was orthogonal. Okay, that's the basic idea. Now, in running this particular type of process here with this, we're using vector projections. We'd like to use matrices this time. So the information that we have on all the grounds in the process, we can actually summarize in this fraction right here. Okay, u times u transpose, where u is one of the grounds that we're going on to each time, but it's thought of as a column vector. So u transpose divided by this scalar right here, which is just the dot product between u and itself, ut u. So instead of thinking about scalars like this, u dot v divided by u dot u, and then multiplying this to u, all right? Instead, actually what we're doing is we're going to build a matrix that we multiplied to v. So there's a little bit of a difference there. The resulting calculation is the same. We're just reorganizing and regrouping the additions and multiplications, really, is all that we're doing. So basically what we do is we can make this and then we can column multiply to v. Now, the benefit of that is that we only need to column multiply to v one time. So we can like add these guys up successively and we can iteratively get a matrix like this, like b1, v2, b2, v3. I mean, look how nice. If we kept on going, I mean, that's how nice each step looks. W4 is equal to v4 minus b4, or b3, that is, b3, b4, where b3 is obtained from b2 just by adding one more thing on. And b2 is obtained from b1 just by adding one more thing on. What do you add? You're actually just adding the matrices. So this is the matrix that we get when u is the ground right here. Let's suppose it's w1 is the first ground. So you put w1 in here and you get a matrix. In fact, that's what this guy is right here, b1, just by putting w1 into that guy. Now what's b2? This matrix right here, we obtain just by simply taking b1 itself and then adding on the ground idea matrix, okay, where u is what we're projecting onto. So this fraction, but instead of using w1, you throw w2 into this guy, okay? So you have the last matrix plus another ground matrix, and that becomes b2. Okay, now you just kind of keep on going. Notice that these b1s, b2s, b3, and so forth do not actually depend at all on v2, v3, v4 in this process, meaning that we can get it completely from the previous calculations here and the previous grounds that we have in our result. I'm just using the word ground to mean something we're projecting onto as we proceed in the process. Okay, so let's just take a look here at what's happening. Let's just walk through the steps. All right, W1 is just going to be V1 right here. W2, how do we obtain it? Well, we take V2 right here and we subtract off a matrix, which is this, times the column vector of v2. So let's walk through that. So how do we obtain this? All right, now first of all, this guy right here in the denominator, that's just the dot product of u with itself. What is u in this case? It's w1. What's the dot product of w1 with itself? Well, it's 2. So that's why we have a 1/2 here. And then the top here, this is the column vector multiplied on the right by its transpose, which is a row. 0, 0, 1, 1, 0, 0, 1, 1. Now, how does this work, this multiplication? Simply think a column interpretation. So like, so each one of these guys is going to be replaced with a column. What column? It's going to be 0 times that column. And then, so 0. And 0 times that column, 0. 1 times that column. So just that 1 times that column. So it just simply looks like this. Not too bad. You can multiply multiply the 1/2 in, or you can keep it separate for now. Okay, but that's B1. All right. So so what we want to do is we just want to matrix multiply. Uh, so we want to matrix multiply V2 as a column on the right of B1. So what does that mean? Here, that just simply means, so as a column, let's think about that. 1, 0, 1, 0. So this simply means that we take 1 times the first column plus 0 times the second column plus 1 times the third column plus 0 times the last column. So basically it's just 0, 0, 1, 1, but with a 0, 0, 1 half, 1 half. So we're taking, so we take V2, and what do? We subtract from V2 0, 0, 1 half, 1 half. And if we, again, that was obtained just simply by multiplying this on the right to that matrix right there. And in the end, we end up getting 1, 0, 1 minus half is a half, and 0 minus a half is negative half. Right, that's W2. We obtained it right away by doing that. Okay, now let's take a look at the next step. We just need to get B2, and then we can make this calculation be done. How do we get B2? Well, we do this again with this ground. Now, what do we use as the ground? We used, okay, so, well, first of all, we basically, actually, we take what we've already done and the matrix that we already have, so this matrix, and we add it on to this one. So we have to add up the matrices that we've used. And if we do this recursively, then we just have to basically add one thing on to what we've just done. Okay, so we have this, and we're going to add on to this what we get from using W2. So the result we just obtained, we're going to now ground it, because the new thing we want it to be perpendicular orthogonal to that guy as well. So we take this guy and we pop it into here. We're dividing by the dot product with itself. And in the process, what do we obtain? We obtain 1 plus a quarter, so which is 3/2. The reciprocal is 2/3. So when you're dividing out by it, it'd be like multiplying by 2/3. And then right here, we throw W2 into, here's a column, and then think of it as a row right here. And what does this mean right here? This means simply take 1 times that column, 0 times that column's right there. So kind of as we look, I mean, this is, what goes in this first column? I mean, this column only has one thing in it. So it's like 1 times the only column there is. So this 1 basically just means take that whole column. The 0 means just zeros. This 1/2 just means take a half of all that. This negative half just means take a negative half of all that. So we get our columns quite quickly that way. I mean, multiplying by column and row is actually fairly straightforward, not too challenging or slow. So we can get this like this, and then we have a 2/3. We can multiply the 2/3 in, we obtain this matrix. Now we just have to add this on to B1. So basically in these bottom 4 areas, we just add on, we add on a half because we have a half multiplied in right there. So we add on a half, and we end up getting this matrix right here. So that's our B2. So let's think about what it means to multiply B2 to B3. So thought of as so think of this right here. We take 1, 0 minus 1, 0. All right. So multiplying that on, what does this mean? This means takes 1 times that column and then subtract off that column. So basically it's just this column minus that column. So we get a third minus 2/3, negative 2/3, negative a third minus a third is negative 2/3. Okay, so we've just obtained this guy. We just need to subtract it from V3. So this minus that. So 1 minus, so we have 1 minus a third is 2/3. 0 minus 0, 0. Negative 1 minus negative a third is negative 1 plus a third, which is negative 2/3. 0 minus negative 2/3 is positive 2/3. So therefore we obtain it, and we've successfully used the Gram-Schmidt process using matrices in this way to obtain our new new orthogonal basis. Thanks for watching.